Welcome to the Deep Dive. We're here to cut through the noise and deliver the core insights from, well, the really essential texts.
That's the plan.
And today, we're strapping in for a journey into Richard Feynman's thinking, specifically Chapter 9 of his legendary lectures on physics.
Newton's laws of dynamics, a big one.
Absolutely. Our mission today is to really follow Feynman's path here. We want to move beyond just, memorizing EFMA.
Right.
And try to uncover the central idea, maybe the central truth of classical mechanics, which seems to be that solving real-world dynamics problems is fundamentally a computational challenge.
Yeah, that's really the essential realization this chapter builds towards. Kinematics, just describing how things move, that's one thing.
The easier part, maybe.
Often, yeah. But dynamics, the study of why things move, that hinges entirely on this concept of force. It's the thing that takes physics from just description to, well, prediction. Real power.
And we should probably set the scene a bit. Historically, I mean.
Yeah.
Before Newton, understanding planets involved complicated rules, right? Kepler's laws.
Very complex geometrical rules, yeah.
But Newton, really building on Galileo's ideas about inertia, he gave us a mathematical mechanism.
Exactly. It wasn't just describing orbits anymore. It was predicting how planets affect each other. Those tiny poles, the perturbations. He basically gave us the engine for the cosmos.
It's a beautiful synthesis, isn't it?
Yeah.
Newton takes Galileo's observation, an object just keeps going straight unless you mess with it, constant velocity.
And makes it the first law. But as Feynman points out pretty quickly, that first law is really just a special case of the second law.
Which is where the real quantitative stuff begins, defining motion properly.
Okay, let's jump right into that second law then, because usually you see it in that simplified form, EFMA. Why does Feynman insist on starting with something else?
Well, because to measure motion properly, you need this quantity, momentum. Momentum, P, is mass times velocity, mv.
Got it.
And Newton's real second law, the fundamental one, defines force as the rate of change of that momentum over time. So F equals dmv dt. Okay, dmv dt, that derivative form, it feels a bit more complex than EFMA. Why is that distinction so important? When do we absolutely need that full version?
You need it whenever the mass isn't constant. Think about a rocket. It's burning fuel, right? It's actually throwing mass out the back at high speed.
Okay. So its own mass is decreasing.
Exactly. If you just used EFMA and treated the rocket's mass as fixed, your calculations would be wrong. The momentum form, dmv dt, correctly handles systems where the mass changes. That's why it's the truly fundamental definition.
That makes a lot of sense. It's the more general case.
Precisely.
Speaking of careful distinctions, mass versus weight. The text makes a point of this. They aren't the same thing, even though we often use them interchangeably. If I stand on my bathroom scale, what am I actually measuring?
You're measuring weight, which is the force of gravity pulling on your mass.
Okay.
Mass itself is about inertia. It's sort of how much stuff is in you, how resistant you are to changes in motion. Weight is just one specific force acting on that mass, the gravitational one.
So an astronaut in space.
Weightless, sure. But they still have mass, still have inertia. It takes just as much effort to push them sideways in orbit as it does here on Earth because their mass hasn't changed.
Right, that makes the difference clear. And that idea of pushing sideways immediately brings direction into it.
Yes. Vectors.
To really do dynamics, we have to use the language of direction.
Yeah.
We need to separate speed from velocity.
Yeah, speed's just the number. How fast? Your speedometer reading.
Magnitude only.
Right. Velocity includes direction. It's a vector. And to work with vectors, you need a frame of reference, a coordinate system, usually x, y, and z.
So motion in 3D is just about how those x, y, and z coordinates change over time.
Basically, yes. Your velocity components are vx, dx, dt, y and z s dt, and vz in d c z d dt. And the speed, that's just the overall magnitude of that velocity vector. You find it using Pythagoras in 3D.
Okay, and acceleration then. We often think of it as just speeding up, but it's more than that, isn't it?
Oh, definitely. Acceleration is any change in velocity. So you can change the magnitude, speed up or slow down, or you can just change the direction.
Like going around a corner?
Exactly. Or the classic example Feynman uses, uniform circular motion, swinging a ball on a string at a constant speed.
The speed isn't changing.
But the direction of the velocity is constantly changing. The ball is always being pulled towards the center. That change in direction is an acceleration.
Centripetal acceleration.
It's the one. And the text gives the formula, v squared over r. That acceleration requires a constant force pulling inwards, even if the speed stays the same.
This is where breaking things down into components really shows its power, right? Force and acceleration are vectors. So we can split the total force, F, into its x, y, and z parts. Fx, Fy is c.
And the magic is the second law applies to each component independently. Fx equals mass times x, phi equals mass times a, and so on.
So you trade one potentially very hard 3D vector problem
For 3 simpler one-dimensional problems. It's a huge simplification strategy.
Let's take that projectile example. An object falling, maybe thrown forward a bit.
Yeah.
If we ignore air resistance, gravity only pulls down vertically.
Right. So the force is only in the, say, the z direction. Helene equals Evli or mg or Jame, depending on your convention.
What does that mean for Fx and Phi?
There's 0. No horizontal force is acting.
And if Fx is 0, then the second law, Fx equals mx, tells us.
X must be 0. The acceleration in the x direction is 0. Same for the y direction.
Meaning the horizontal velocity doesn't change, it's constant.
Exactly. The vertical motion under gravity is completely independent of any horizontal motion you started with. That's why, the classic physics problem. A bullet fired perfectly horizontally and one just dropped from the same height.
They hit the ground at the same time.
Because the horizontal motion doesn't affect the vertical fall at all. Components keep things separate.
Okay, so we have this powerful framework, FMA, applied component by component. But now we hit what Feynman calls the big question. What is the force?
Yeah, the laws tell you what acceleration a given force produces, but they don't tell you where the force itself comes from or what its formula is.
So to actually solve a problem, like predicting motion, you need more. You need the specific force law for that situation.
You do. You either derive it or, more often, you look it up based on the physical interaction. The chapter gives us 2 key examples.
First one, gravity near the Earth.
Which, for objects near the surface, we approximate pretty well as just F equals mg. The force is constant, pointing down, proportional to the mass. G is the acceleration due to gravity.
Simple enough for many problems. And the second example.
Springs. Hooke's law. The force from a spring is proportional to how much you stretch or compress it. F equals mass kx.
Where x is the displacement from the equilibrium position. And that minus sign is important, right?
Crucial. It means the force is always restoring. It always pulls or pushes back towards the equilibrium point. Stretch it out, it pulls back. Compress it, it pushes back.
So these formulas, like mg or mass kx, they're the inputs we need to feed into Newton's second law.
Exactly. You plug the force formula into ESMA, so for the spring you get m times acceleration equals mass kx, or acceleration equals mass Galileo times x.
And that equation relates acceleration, the second derivative of position to position itself. That's a differential equation, isn't it?
That's what it is. Dynamics problems almost always lead to differential equations. They link how something changes, like velocity changing, which is acceleration, to its current state, like its position.
Now, solving these equations with calculus, finding a nice, neat formula for xt, that can be hard.
Sometimes incredibly hard, or even impossible to do analytically with just formulas, especially if the forces get complicated.
And this is where Feynman pivots, doesn't he? He moves from the elegance of the laws to the practical necessity of computation. He introduces the numerical method.
Yeah, it's almost the unsung hero of the chapter. If you can't find an exact continuous solution, you approximate it step by step.
Using tiny little time intervals, he calls the interval epsilon ace.
Right. The core idea is surprisingly simple. If you know where the object is, position x, and how fast it's going, velocity v, at a specific time t,
you can use the force law like Fkx to calculate its acceleration, a, right at that moment, because a Fm.
Exactly. You know the acceleration now. So you make an assumption. You assume that acceleration stays roughly constant over the next tiny time step.
Okay, a small approximation.
Then you just project forward. The new position at time t plus a is going to be the old position plus how far it moved in that small time, which is roughly velocity times a, xt plus vt.
Makes sense.
Yeah.
Old position plus change in position.
And the new velocity, it's the old velocity plus the change in velocity, which is roughly acceleration times vt plus a.
And you do it again.
And again and again. You use the new position and new velocity to calculate the new acceleration, then take another step. It's iterative. You're essentially tracing out the path piece by tiny piece.
Like connecting the dots, but the dots are calculated one after another.
A pretty good analogy. The chapter shows this for the spring problem, calculating the oscillations step by step. It even shows, in Table 9-1, how you need some refinements, like maybe using the velocity halfway through the interval to make the approximation really accurate.
So it's not just a theoretical idea, it's a practical calculation technique.
Absolutely. It demonstrates that even if the differential equation is nasty, you can still get a very good numerical answer by breaking it down into these simple, repeatable steps.
Which brings us to the grand finale of the chapter, the ultimate application.
Planetary motion, calculating orbits.
This is what Newton was really aiming for, wasn't it? Applying his laws to the heavens. Here, the force law is Newton's universal law of gravitation.
Right. The force between, say, the sun and a planet is proportional to the product of their masses, m for the sun, m for the planet, and inversely proportional to the square of the distance, r, between them. F is proportional to m4.
The famous inverse square law.
Yes. But now, to use our step-by-step method, we need that force in component form again. The force points towards the sun, which we can put at the origin.
So if the planet is at coordinates x, y, the distance r is squared xy plus y.
Correct, and the force components get a bit more complicated. The x component of the force, Fx, turns out to be xdgm apply xyo, and phi is sgm times eo.
Hold on. Y r cubed in the denominator. The force law is inverse square, 1r real. Where does that year come from? That always trips me up.
Good question. It's because the 1r real gives you the magnitude of the force vector. To get the x component, you need to multiply that magnitude by the cosine of the angle the position vector makes with the x-axis.
Okay.
And the cosine of that angle is just x divided by r, adjacent over hypotenuse. So you multiply the magnitude, proportional to 1r real, by the directional factor, xr. That gives you x sorero. It's how you correctly project the central force onto the x and y axes.
Got it. That makes sense. It combines the magnitude and the direction properly.
Exactly. So now you have these component force equations, x and free, that depend on both x and y and involve r. They look complicated.
But the solving method is the same.
The numerical method is exactly the same. You know x and y, you calculate r. Then you calculate x and phi using those r formulas. Then you get x and free and x, xm and a, and x and free.
And then you do the stepping forward, xt plus at plus vxt plus ext plus xt, and the same for y and v.
Precisely. The chapter shows a table, Table 9-2, where they actually do this calculation with a small time step, equals 0.1, and you can literally trace the planet's xy coordinates as it moves in its orbit.
Wow. So the same simple step-by-step logic handles something as complex as an orbit.
And this is where you really appreciate the scale. Calculating one planet around a fixed sun is already work. But the real solar system...
All the planets pulling on each other simultaneously.
Yes. You have to calculate the force on, say, Earth by summing up the individual gravitational forces from the Sun, Jupiter, Mars, Venus, everything.
Yeah.
Every single time step, the complexity just explodes.
And Feynman mentions the accuracy needed, trying to predict Jupiter's position to 1 part in a billion over one orbit.
Yeah. To get that kind of precision, your time step has to be incredibly tiny. You end up doing millions, maybe billions of these simple calculations for just one trip around the sun.
It really drives home the point that these simple, elegant laws, Newton's laws, the law of gravity, their predictive power is fully unlocked only through massive computation.
That's the profound takeaway, I think. Classical mechanics isn't just about finding neat analytical solutions anymore. It's about the practical, iterative application of these fundamental rules, step by painstaking computational step, to model the universe.
So let's recap this deep dive into dynamics. We kicked off seeing dynamics as the study of why things move, built on the concept of force.
Defined fundamentally through momentum, F equals dmv dt.
We saw the power of vectors and components, breaking down forces and motion here into manageable x, y, z parts.
Fx max, mabulus may, etc.
We recognize the need for specific force laws like gravity, mg, or springs, nec is x, as essential inputs.
Because Newton's laws alone don't tell you what the force is.
And finally, the big reveal. Solving the resulting differential equations for real-world systems, from springs to planets, often demands numerical methods, iterative, step-by-step calculation.
Showing that this incredibly complex dance of the cosmos can be simulated with a remarkable precision, starting from just those basic rules and a whole lot of calculation.
Which leaves us with a final thought, pulled straight from the implications of the text. The accuracy of our entire calculated universe seems to hang on that little time step in image. We choose how small to make it.
A trade-off between speed and precision.
Exactly. So how does that fundamental trade-off, inherent in the method, shape what we actually mean when we say we know or understand the workings of the cosmos? Something to chew on.
Definitely something to think about. It connects the deepest laws to the practical limits of computation.
Well, thank you for joining us on this deep dive into Feynman and Newton's dynamics.
Always a pleasure. We'll see you next time.